Hi, I'm Mark Barsamian. In this video, I'll be continuing a discussion of continuous income streams. I'll be discussing what's called the future value of a continuous income stream and the present value of a continuous income stream. This material is from section 6.2, Applications in Business and Economics. That's referring to applications of the definite integral in business and economics. More specifically, the reading is from the top of page 402 to the bottom of page 403, example 4. The corresponding homework is this collection of 5 exercises from section 6.2. Recall the formula for continuously compounded interest. An account with continuously compounded interest has balance described by this equation. Capital A equals capital P e to the RT. Capital P is the amount of the original deposit, called the principal. Little r is the interest rate expressed as a decimal. Little t is the time in years since the original deposit. Capital A is the account balance at time t. Also recall the useful indefinite integral rule. The indefinite integral of e to the kx is e to the kx over k plus c. It's helpful to remember that with the corresponding derivative rule, that the derivative of e to the kx is k times e to the kx. And recall the idea of a continuous income stream from the previous video. A continuous income stream is an idealized way to think of a source of income. For example, a job that pays monthly paychecks of $10,000 each could be thought of as an income stream with a continuous flow rate of $120,000 per year. And also recall the idea of total income from a continuous income stream. It was the answer of this question that was posed. What is the total amount of income that flows in during a time interval from A to B? We visualize that question with this picture involving a bucket. Money flowing in, money accumulating in the bucket. Capital A, parentheses T, denotes the amount of money that's accumulated in the bucket. Little f of t denotes the flow rate of money flowing into the bucket. The answer to this question, what's the total amount of money that flows in, was this integral formula. The total income, delta A, is equal to the definite integral of the flow rate. And I should abbreviate the total income as capital TI. We'll start the discussion for the current video by discussing what's called the future value of a continuous income stream that earns interest. In the discussion in the previous video of the total income from a continuous income stream, we were concerned only with the amount of money that accumulated in the bucket, the quantity capital A parentheses T. Now consider a more complicated situation. Suppose that the income stream with flow rate little f of t flows into an account that earns continuously compounded interest with interest rate little r. As with the discussion of total income from a continuous income stream, we can visualize this more complicated situation with a picture showing money flowing into a bucket. So money that has flowed into the bucket, supplied by the continuous income stream, is shown in green. So that's money that flowed in from that continuous income stream. Once the money lands in the bucket, it starts earning interest, which is shown in red. Now, a natural question is, if a continuous income stream flows into an account that earns continuously compounded interest at rate little r, what will be the balance of the account at time capital T years? Note the capital T. This balance is called the future value at time capital T years. That's abbreviated capital FV. Finding an answer to this question is actually tricky. Note that the continuously compounded interest formula, capital A equals capital P e to the RT, is used in a situation where a single amount, capital P, is deposited and a particular time, little t, elapses. Consider the current situation with money flowing into a bucket and then starting to earn interest only after it arrives in the bucket. Well, some of the money in the bucket will be in the bucket for a long time, earning interest for a long time. But some of the money will arrive in the bucket shortly before time capital T. That late arriving money won't earn interest for very long. In other words, there's not just a single deposit, and there's not just a single elapsed time. So finding the answer to this question, what will be the balance of the account at time capital T years, finding the answer to that question is difficult. It turns out that the answer to the question is a complicated looking integral calculation. It's presented here in this green box, the future value of a continuous income stream. A continuous income stream has flow rate little f of t, and the time interval is t goes from 0 to time capital T, and the income flows into an account that earns continuously compounded interest at rate little r. Then the future value, denoted capital FV, at the end of capital T years is given by this integral calculation. So notice in this integral calculation, there's the familiar term for the flow rate, little f of t, and then there's this other term, e raised to the quantity little r times the quantity capital T minus little t. That's a mess. That term is a term that accounts for the fact that different portions of money in the bucket have been in the bucket for different amounts of time, and as a result, they'll have earned interest for different amounts of time. Let's start with an example. We'll do a special case, the future value of a continuous income stream that has constant flow. So in this example, we'll suppose that a continuous income stream has flow rate little f of t equals C dollars per year, so constant flow, and it flows into an account that earns continuously compounded interest at rate little r. The question is, how much will be in the account at time capital T years? That is, what is the future value at time T years? Well, we're going to use this integral calculation to find the answer. The result is here. It's quite messy. I'm actually not going to go through the details of this. It's the usual stuff. We put in the formula for the flow rate, that term constant flow. We use the fundamental theorem of calculus to let us replace that definite integral calculation with an indefinite integral calculation. The details of the indefinite integral calculation are on the next page. There's a lot of simplifying that goes on, and in the end, the result is this. The future value is this expression, little c times the quantity e to the little r capital T minus 1 over r. There are the details of the indefinite integral calculation. Again, lots of steps. I won't go through the details. You'll see, though, some things that are familiar, such as this. The indefinite integral of e to the kt is e to the kt over k, and so forth. But the result is very useful, and we'll put it in a green box for future reference. So the future value of a continuous income stream with constant flow is given by this expression. Example 2. This is similar to one of your homework problems. Suppose you deposit $1,500 a year into an account that earns 3.5% interest, compounded continuously. Treat the yearly deposits into the account as a continuous income stream. The question is, how much will be in the account 40 years later? Well, we can use the result of example 1, this expression. With these particular values, the value of little c is 1,500, that's the constant flow rate. The value of little r is 0.035, that's the interest rate expressed as a decimal. And the total time elapsed is capital T, 40 years. The result is here. Here's the exact answer. And here's an approximate answer, rounded to the nearest dollar. Question B, how much of the final amount is interest? Well, it'll help to visualize this question using the bucket. We found that the future value is roughly $130,937. We're being asked to find the portion of that amount that's interest. In terms of the bucket, it would look like this. We found this future value. That's the total amount of money that will be in that bucket at time 10 years. And we're being asked to find how much of that money was interest. Well, the key to this is to notice that the stuff in that bucket that's not interest is this green region at the bottom. That's money that flowed in. That's not interest that was earned. That's just money that flowed in. Well, the amount of money that flowed in during that time interval is called the total income. We learned how to compute total income in the previous video. So what we need to do is compute the total income and then subtract the total income from the future value to get the amount of that interest. The total income is easy to compute because the income stream has a constant flow. So the total income is just simply the flow rate times the elapsed time. So $1,500 times 40 years. So $60,000 is the total income. Therefore, the portion of the future value that's interest is this. Compute interest by doing future value minus total income. So that $130,937 minus $60,000 of total income. The result is the interest is $70,937. So in this picture, the future value is this amount, and that's made up of $60,000 of money that flowed in and $70,937 of interest. Let's go on. Example 3. We'll consider another special case, future value of a continuous income stream with exponential flow. So in this example, we're supposing that a continuous income stream has exponential flow rate, little f of t equals c e to the kt, and it flows into an account that earns continuously compounded interest at rate little r. The question is, how much will be in the account at time capital T years? That is, what is the future value, capital FV? Well, the integral calculation we'll do is on the next page. There's the general form for future value, that messy integral calculation. There I've put in the exponential flow, and the rest is just very messy calculus, but the usual kind of approach. We have a definite integral to do. The fundamental theorem of calculus tells us that that definite integral can be found by doing an indefinite integral calculation. The indefinite integral calculation is done on the next page and brought back. You can see that it's quite messy, all of this. Now there's a lot of simplifying that goes on. One thing that happens is, of course, the constant of integration gets canceled in the subtraction step. Another bit of canceling that happens is here. This RT cancels that RT. We combine these terms because they have a common denominator. And then I do kind of a random thing. I change the order of the subtraction in the numerator and in the denominator. So the result is I don't change anything, but I just change the way the formula looks. The indefinite integral details I won't go through completely, but there are a couple of things that are worth noting. First of all, there's the simplifying of the exponential expressions. R times capital T minus T can be written as R times capital T minus R times little t. Furthermore, this term can be written as e to the r capital T times e to the minus r little t. This term is constant, so it can be pulled out front. The other terms that involve the variable little t are this term and this term. They can be combined into a single term here. So there are lots of algebra steps here involving exponential functions and rewriting them. I haven't even shown all of them, and still there are a whole lot of steps here. It's worth going through this. Another thing that's important is that there is a constant of integration that shows up, this plus d. It gets multiplied. This c e to the rt gets distributed, and I end up with this term, c e to the r capital T times capital D. Now remember that capital D can be any real number. So that means that c e to the rt times capital D can be any real number. So we might as well just introduce a new symbol that can be any real number. So we introduce a new symbol for a constant of integration. That's that capital E. This is a very long, messy calculation. It's worthwhile to notice that the result actually agrees with the previous result for a special case. That is, if this exponential flow, c e to the kt, has k equals 0, then the result that we just got simplifies. If we use k equals 0, then the whole expression simplifies to this. That's the result that we would expect, because if k equals 0, then the exponential flow is actually a constant flow, because e to the 0t is just e to the 0. That's just the number 1. The flow would be f of t equals c. And we found the future value for a constant flow with a flow rate c in example 1, and we got this exact same formula. So our messy formula that we just got for the future value of an exponential flow reduces to the simpler case of the future value for a constant flow in the special case when k is equal to 0. So that gives us some confidence both in our current result, which is this messy thing, and our earlier result, which was this simpler expression. Now the result from the current example is useful enough that we should put it in a green box. So here is the future value of a continuous income stream with exponential flow. If you have a continuous income stream with exponential flow rate given by this formula, c e to the kt, dollars per year, and it flows into an account that earns continuously compounded interest at rate little r, then the balance of the account at time t years, that is the future value at time t years, will be this expression. Example 4 is similar to 2 of your homework problems. Find the future value at 4.5% interest, compounded continuously for 10 years, of a continuous income stream with flow rate f of t equals 1,500 e to the minus 0.03 t dollars per year. Give an exact answer and a decimal approximation, rounded to the nearest dollar. Well, this is exponential flow, so we can use the formula from the previous example. This formula. We'll use it with the particular values. C equals 1,500 from there. K equals minus 0.03 from there. Little r is 0.045. That's the interest rate expressed as a decimal. And the time is 10 years. If we substitute those terms into this messy expression, we get that, and we simplify a bit. There's the exact answer, and there's the approximation rounded to the nearest dollar. Question B. Compute the portion of the future value in Part A that's money from the income stream and the portion that's from interest earned. Well, this is similar to a question that we had earlier. So the future value is this amount, and we're being asked to find the portion of that that's interest and the portion of that that's money that flowed in. Well, realize that the money that flowed in during that time interval is the total income. So we're being asked to find the total income and the interest earned. We start by computing the total income by integrating the flow rate over the interval from 0 to 10. Here's the definite integral calculation. It's the usual messy calculation. I won't go through this because it's the same format of previous similar calculations. The result is the total income is $12,959. So that's that green portion of the money in the bucket. There are the indefinite integral details. I won't go over them. It does have the key step, though. Indefinite integral of e to the kt is e to the kt over k plus c. So we found that the total income, the green portion of the money in that bucket, is $12,959. So now we can compute the interest. We simply subtract that total income from the future value to get the interest. The result is the interest is $35.91. That's the end of that example. Example 5. This is similar to one of your homework exercises. An investor is presented with a choice of two investments, investment A or investment B, and they can be bought for the same price. Each investment produces a continuous income stream. The flow rate of the income stream from investment A is this, $10,000 per year. That's constant flow. The flow rate of the income stream from investment B is this. G of t is 9,000 e to the 0.03 t dollars per year. So that's exponential flow. Both income streams will flow into an account that earns 5% interest compounded continuously. So the goal here is to compare the future values of these investments to determine which is the better choice over the next 10 years. Well, to compute the future values, we'll use the formulas for the future value of a continuous income stream with constant flow from example 1 and the future value of a continuous income stream with exponential flow from example 3. To find the future value of investment A, we'll use the result of example 1, that's constant flow. With these particular values, the constant flow rate is $10,000 per year, the interest rate is 0.05, the time is 10. We substitute those into the formula from example 1, and we get this expression, which simplifies to this exact answer. The approximate answer rounded to the nearest dollar is this. Approximately $129,744. To find the future value of investment B, we use the result of example 3 with these particular values. C is 8,000 and K is 0.03, because remember the flow rate was 8,000 e to the 0.03 t, exponential flow. We have the same interest rate because both of these flows are flowing into an account that earns 5% interest compounded continuously. The time interval is 10 years. So then we use the formula from example 3. With those particular values, we get this expression. We simplify it to this final exact answer, and then plug that into a calculator and get the decimal approximation, $119,545. Well, conclude that investment A is the better investment. Investment B has a future value of $119,545. Investment A has a future value of $129,744. Go on. Our final topic for this video will be the present value of a continuous income stream that earns interest. I see that I've got a typo in this paragraph. So recall that when we were discussing the future value of a continuous income stream that earns interest, we saw that an issue that complicated the computation of the future value was the fact that money that flows into the bucket starts to earn interest with interest rate R only after it arrives in the bucket. Some of the money in the bucket will be in the bucket for a long time, earning interest for a long time. But some of the money will arrive in the bucket only very shortly before time capital T, and that late arriving money does not earn interest for very long. A natural question is this: how large would a one-time deposit need to be at time 0 into an account earning continuously compounded interest with interest rate R to have the same value, capital FV, at that later time, capital T, the same value as an account that has continuous income stream with flow rate, little f of t, that earns interest with interest rate R over this time interval from 0 to t? That's a mouthful. It might be better to just say all that again with a picture. So here's the question. We have this idea of a continuous income stream with flow rate little f of t in some time interval from 0 to t. And at the end of that time interval, some money has flowed in, that's the total income, and some interest has been earned. The question is, if we are going to make a single deposit at time 0, and it would sit in the bucket for the entire time interval, capital T, earning interest, how much money would we need to deposit at time 0 in order to have the same value at time capital T? The same value as this other case where money is flowing in over the whole time interval. Well, that answer to that question is given a name, the present value of a continuous income stream. So the present value of a continuous income stream, those words are used in the situation where you have a continuous income stream with flow rate little f of t, and it flows for the time interval from 0 to capital T, flows into an account where it earns continuously compounded interest with interest rate R, resulting in a future value capital FV at that later time capital T. Well, what these words, the present value, mean is this. They mean the size of a one-time deposit that would be made at time 0 into an account that earns continuously compounded interest with interest rate R. The amount of that one-time deposit that would result in an account balance equal to capital FV at time capital T. So again, the present value is the size of this single deposit at time 0 that results in an eventual balance that's the same as the future value of this continuous income stream with flow rate little f of t that flows over that whole time interval. Notice that the present value, this quantity, does not need to be as large as the total income from the continuous income stream. Why? Well, if you think about it, all of this blue money sits in that bucket for the entire time interval, capital T. So it earns a lot of interest because it's all sitting in the bucket for a long time. Whereas this green money that flowed in from that flow, a lot of that money arrives later in the time interval, or even very late in the time interval, right before time capital T. And so that later arriving money doesn't earn as much interest, doesn't sit in the bucket for as long. So you'll have to flow more money into the bucket because you're going to have less interest earned because not all the money sits in the bucket for very long. So we expect that this present value, whatever the value is going to be less than the total income, whatever it is. So here's our final example for the video. This is similar to one of your homework problems. An investment will produce a continuous income stream with flow rate f of t is $12,000 per year for 10 years, flowing into an account where it will earn 6% interest compounded continuously. So question A is, what is the total income of the income stream? So this is asking, what is this green amount? Well, that's easy. The income stream has a constant flow rate. F of t is $12,000 a year. The income stream flows for 10 years, so the total income is just the flow rate times the number of years, so 12,000 times 10. The total income is $120,000. That's that green amount in the bucket. Question B is, what's the future value of the investment? That's asking, what is this whole amount? Well, this income stream has constant flow, so we can use the result of example 1 with particular values. Little c is 12,000, that's the constant flow rate. Little r is 0.06, that's the interest rate expressed as a decimal, and capital T is 10. The result is, using that formula from example 1, substituting in those numbers, we get this expression. We simplify, we get this exact result, and then type that into a calculator to get this decimal approximation rounded to the nearest dollar. That amount, $164,424, is the amount of money in that bucket, including all the green money that flowed in and all the red interest that was earned. Question C, what is the present value of the investment? Well, the question is asking how big an initial deposit needs to be into an account that has that same 6% interest rate compounded continuously for the account balance to be equal to that future value after 10 years. Well, for this, remember that the continuously compounded interest formula is this. Capital A equals capital P e to the RT. Now we know these values. We know that we want the final value to be $164,424. We know the interest rate. We know the elapsed time is 10 years. What we don't know is the principal. We don't know how much money we would need to deposit at the beginning. That's what we need to find. Capital P, the amount of the initial deposit. Well, we start by solving the continuously compounded interest formula for capital P. So here's the continuously compounded interest formula. We solve it for capital P just by dividing by e to the RT. There's the formula that we'll use to find capital P. We substitute in our known values. We get this exact answer. And then this decimal approximation rounded to the nearest dollar. The result is the present value is $90,238. Notice that the present value is significantly smaller than the total income. So the present value was $90,000. The total income was $120,000. Both produced a future value of $164,000. After 10 years, the continuous income stream will have flowed in $120,000 of total income. It will have earned this amount of interest. The present value money, that $90,000, gets deposited in a single deposit at time zero. All that money sits in the account for 10 years, earning a lot more interest. That's why this investment, single deposit at time zero with a smaller initial deposit, can have the same value at time 10 years as this continuous income stream with the flow rate that flows continuously for the entire 10 years. That's the end of the example, and that's the end of the video. Thank you.